G'day, Lance from Motive Power, back again to talk a little more in our series about off-highway vehicle design. Today we're going to look at some real-world examples, and particularly heavy haul vehicles. These, they work hard. They're required to supply high power, high tractive effort for long distances, and that makes them a little bit unusual. You need to have very good cooling and very good reliability. They could be something like an M1070, a heavy equipment transporter, or something like a Found Goliath. Vehicles like this exist all over the world. They're not uncommon, but they may be out of your normal sight. One of those examples is aircraft towing tractors. You might think of them as the little vehicles that run around under the jumbo jet that you're about to get on. I assure you, they're not little vehicles. They're big, heavy, complicated, and they're a damn good example of heavy haul vehicles. So we're going to use them as a sort of worked example today. So what do they look like? Well, they look like this. That's a Fox F1450 towing an RAF combi tanker. And I'm concentrating today on conventional towing tractors with a tow bar. Tow bars like this that are hitched between the tractor and the aircraft. And they're not quite as simple as you might think, but we'll get to that a little later. We're specifically not going to talk about tow barless aircraft towing tractors, things that actually pick up the nose gear and drag the whole aircraft away. To me, these are, they're too damn complex for what they need to do. But we're just not going to talk much about them today. If you've got a big airline and you want big sexy equipment, the chances are you'll go to tow barless because you think it's sexy. But there are other alternatives. So this is one of those things that you might think is a small tractor. Again, a Fox F1450, 450 horsepower on board, 54-ton mass, and able to cope with a gross combination mass of over 550 tonne. That's 1.2 million pounds for Americans. So not only are the tractors big solid things, they're powerful and they're capable of handling very big loads. One of the issues with a towing tractor application is it needs to tow the aircraft. That's an obvious thing. But I'm firmly convinced that aircraft manufacturers forget completely about the tow bar attachments until they're ready to haul their prototype out of their first hangar. And then they go, oops, what did we forget? Let's put the simplest thing on. What that means is we have an array of different tow bar hitches on aircraft nose gear. And that can be good in order to segregate aircraft sizes, but generally it complicates the whole process. So as I showed you earlier, aircraft towed with a tow bar. It's not just a straight pipe. It is fitted with a head that's suited to the particular type of nose gear attachment. But there's more to it than that. It's hidden. These things have shear pins in them, so you physically can't overload the nose gear. Whether you're pushing or pulling, there are shear pins that will limit that longitudinal thrust. But there are also shear pins that will limit the torque on the nose gear, i.e. the steering torque, and they will fail as well if the load is exceeded. One hopes, though, that the right shear pins are fitted for the right aircraft, and that's not so easy to cross-check. So I'm also not going to talk about pushback tractors. Towing tractors generally get used to push back and tow away an aircraft, and that pushback is from a jetway at a terminal. Done right, it's downhill. You push it back downhill and you tow it away. That's not always the case. Airports aren't really designed for tractors, but it's a consideration that should be made. The reason I'm not going to talk about pushback tractors, well, there's a couple of them. I'll show you. We'll use an example. This is an FMC unit. Pushback tractors are a niche. They have the advantage in that they can be made cheaper and smaller because they don't have to be so durable. Their duty cycle is very much a spike, a load, and then sit back and idle. Or push back for 50 metres, drive forward unladen for 50 metres and wait till the next pushback. Towing tractors, however, have to tow long distances. And it could be 5 or 8 kilometres to a maintenance hangar or from parking area to the terminal, so forth. If you think 5 and 8 kilometres isn't a long distance, if you're only doing 5 or 8 kilometres an hour, it's an hour's at full power, working hard. So what happens with pushback tractors? You can uprate the engine and the axles and the transmissions because the duty cycle is not continuous. Cooling system can be smaller and so forth. What that means is you end up with a more compact tractor, a shorter wheelbase, therefore more manoeuvrable, and it can be higher because it's never going to be used under fuselage. So again today we'll talk about aircraft towing tractors, not pushbacks and not tow balas. That's probably been a little pedantic, but maybe you'll understand as I go through all this. This is yet another application where you need to understand the application and all the things that go on around it. Like most applications, most industries, there's some fudge factors that are used in it. So we're going to talk about it. This is specific for aircraft towing tractors, but it'll be similar for on-highway. So let's look at the whiteboard. So the first thing you need to know is what is the GVM of that tractor going to be, because that's what's going to give you the tractive effort to do the heavy hauling. And there's factors in play. On an airport, the grade is a maximum of 2%. That might seem really, really flat, but it's not. If you're hauling a 400 or 500 ton aircraft, it's significant. In fact, for a 492 ton A380, that's about 10 ton of grade resistance. The next one is rolling resistance. And that's also 2%. So another 10 ton. But before you get it rolling, you have to break away. And that actually consumes more energy to deform the tyres into a rolling format. And that factor's 4%. And with an aircraft towing tractor that's pushing back to commence a tow forward, you need to consider jet thrust. It will depend on what aircraft engines are fitted, but it's typically about 1%. So in total, you're going to push back and tow away, your vehicle needs to be designed to push back up a 2% grade against 4% breakaway resistance and a 1% engine thrust. That's 7%. If you're already rolling, you've probably only got to worry about the 2% rolling resistance. So much harder to get things started than to keep them going. And this is the key design condition. This is what will determine your tractive effort. This is where your power will be determined. So it's reasonably simple to work out what tractive effort or drawbar pull is required to move the aircraft. 7%. But that is a fudge factor. That's industry fudge factors that are applied globally. And the bottom line is no one will let you play with their multi-million-dollar aircraft to determine a more accurate figure. So you have to go with those numbers. You do get some data from aircraft manufacturers, but you have to be very careful about how you apply it. Aircraft manufacturers are aircraft manufacturers. They're not aircraft towing tractor manufacturers. And there's a difference in skill set and perhaps knowledge. So let's look at a few examples of what can be available, and you might have to push your client to get this sort of data. Here's some Boeing information. And this is the total traction and the drawbar pull. If you like, the weight of the vehicle and the drawbar pull at different coefficients of friction. And I've often used 0.57 as wet concrete. But on test with heavy aircraft towing tractors, we never got less than 0.8. And 0.7 or thereabouts was a safe figure to use. So this is some data that is available and might be of use to you. This is some Boeing info for the nose gear attachment. So dimensions, heights, pin diameters and so forth, so you can define the tow bar to be used. Now a tow bar isn't normally made by a tractor manufacturer, but what is important is the hitch height. You try and match that on your aircraft. Unfortunately, because towing points seem to be the last thing designed on aircraft, everybody's got a different height and you end up trying to find an average. Now Airbus were very conscientious when they were working on the A380, and they provided quite a bit of information and they did a lot of tests. Unfortunately, they were a little bit poorly directed. There's data available, but all it does is give you a little bit of guidance. So you can see the factors they've used. This is essentially very similar to what I've used and suggested. The difference is again in coefficient of friction. They've used 0.57 and come up with a 67-ton towing tractor. But they've also said the figures were too conservative. Now, my experience towing on wet concrete, uphill, against engine thrust, a fully laden A380, 54-ton tractor did it fine. Like Boeing, Airbus provide attachment details. They've all got these fancy names, but this is how you attach to a nose gear. Here's some dimensions. This sort of data is available for every aircraft type. Again, here's some A380 information, breakaway resistance, and that's fantastic. That is solid data that you can use. From memory though, they didn't do it at full load. And for a more general look, every aircraft has this sort of data available for airport planning. Not a great deal in these things about towing, but it does make it does get mentioned. So as usual in an engineer's life, there's some guidance, some fudge factors, but you need to decide what you're going to employ yourself. And it will be a risk-benefit analysis. If I'd designed towing tractors to a coefficient of friction of 0.57, they would have been so big, heavy and expensive no one would have bought them. If I designed them for a coefficient of friction of 0.8, they'd be nice and light and would have left the company at some risk that in some circumstances that would be not a sufficiently heavy tractor. So there's always a cost-benefit trade-off. You'll have to work it out for yourself, understanding that there are risks in over-designing and in under-designing. One's technical and one's commercial. So you now know the drawbar pull that's required to pull an aircraft, 7%. So does that let you calculate how big the towing tractor can be? We take that number, divide it by the coefficient of friction, we end up with a tractor mass. Yeah, that's really easy to do. But you've forgotten one important thing. You've also got to move the tractor. So you actually need to work out the tractive effort required to move the aircraft and the tractor. And if you're talking about a 50 plus ton tractor, you've still got sufficient weight there. It does make a difference. If you're talking about moving a Boeing 747-400, you're going to need about 54 ton. You can calculate that using an iterative process, do it in a spreadsheet, come up with a formula, but you need to understand what you can get away with the coefficient of friction. So essentially, tractive effort divided by the coefficient of friction will give you the tractor mass, the gross vehicle mass. So let's look at a worked example, and that would be a Boeing 747-400 at 408 ton. Don't know how many pounds that is, but it's ton. And that's maximum taxi mass, not maximum takeoff mass, not maximum ramp mass, maximum taxi mass, because you're actually going to help the aircraft taxi. So we start with 408 ton. Boeing 747-400. Bit lighter than the A380. We'll go through all the factors that we've previously considered. And let's go 2% grade, 4% breakaway, and 1% thrust. If you do all the numbers, totaling that up, do the analysis, you'll end up with around 50 ton. Actually, probably just a little bit over, depending on what mu you want to use. You will get more than that if you use 0.57. I'm going to assume that we're at 54 ton, because that's the tractor we've been using as an example, an F1 450. That figure assumes all-wheel drive, load equally on all four wheels. If it was 4x2, for example, that would have to be the mass on the drive wheels. So now we know how much mass we're going to need. We can select the tyres. Remember, the first video in this series was tyres. And we used some examples like this. So for this unit, we generally ended up with 1825, 32 ply rating at 131 psi. That figure came from the tyre and rim standards and all the factors for slow speed and only using it on hard standing and so forth. Without those factors, this tyre size would have grown significantly and we would have had trouble fitting it under the aircraft. That tyre size gave us a static loaded radius and a rolling radius and a height, vehicle height, that we could live with. It also gave us the right ground clearance. We had discovered with a previous tractor that was supplied a little bit too heavy that there are lots of 6-inch high power points all over the airport. These are concrete encased. Didn't bother the tractor, but since we only had about 140 millimeters of ground clearance, the tractor was slicing off all the power points. We fixed the, just an end there. We fixed the ground clearance by correcting the weight of the tractor, and we didn't have any further problems with power points. But it's an example that you need to know you've got the right tyre for the right weight. From that time on, we were very careful to weigh the tractors and make sure we knew where the centre of gravity was. And here's an example of tyres selected that way. As you'll see, they're a hard rock lug and they work quite well. So now with the tyres selected, you know the static loaded radius, you know the torque that's required on the axles, and that means you can design or select the axles. In that case, they were Rockwell PSC 1875s, big planetary drive axles, and I do mean big. Hydraulic drum brakes, because the machine ended up completely hydraulic with no pneumatics, and hydraulic dry disc brake on the pinion as a parking brake. And now it's possible to design or select the engine, because you know the tractive effort that's required, usually rattling along on the level, trying to go fast. The tractive effort is just, or the power is just the tractive effort times the speed, and you'll end up with power at the wheels. We've already talked about driveline efficiencies and how to actually arrive at what installed engine power you need. In this case, 450 horsepower. These days you also need to be aware of emissions. In Australia at least, this category of vehicle doesn't have emissions limitations. But we were exporting these vehicles at least one a month to all over the world, particularly in Asia. And we had to be very careful of what the emissions requirements were there and what fuels were there. Fortunately, the emissions were not regulated. We also had to fit that size of engine into the low height, and that's where two-stroke diesels came in. Detroit Diesel 8V92 TAs. They not only provided the power, but it was compact enough to fit in the low height tractor. And now it's time to select the transmission. Because it's a towing tractor, it's going to spend most of its time going forward. But it also needs equivalent performance in reverse, at least for tractive effort, not speed. We wanted it automatic, we wanted soft shifting, and we wanted a global brand so it could be backed up wherever the equipment was exported to. We also needed a configuration that would take a transfer case. And that ended up as an Allison CLT 755 DB, the DB indicating it was configured for a drop box. Allison had their own drop box. We didn't use it because it didn't have an interaxle differential. And here's a typical view of it. Big transmission, but a typical automatic torque converter in the front, and here's the flange ready for the drop box. We were able to adapt our own transfer case onto that flange. So being a towing tractor, when it came to steering, clients wanted it all. Two-wheel steer, four-wheel steer, crab steer, and the occasional rear two-wheel steer. So 4 modes had to be designed for. We went hydraulic because that was simple. and we used an electrically driven pump for emergency steering. If your engine stopped while you were towing, you could hit the big red button and get a few minutes worth of hydraulic power for steering to bring the equipment safely to a halt. Now the chassis was different. It was made of 80mm plate. There's about 35 tonne of chassis. Everybody thinks we should use water or concrete for ballast. They are not dense enough. Lead is, but it's too damn expensive. These tractors, like any low height vehicle, are all about packaging, trying to cram as much into the available volume. So to do that, we used 80mm plate as a chassis. The trick was to not put 80mm welds on it. After assembly of the tractor, it was carefully weighed, centre of gravity determined, and trimming ballast was fitted, usually in a pre-built enclosure, and it was typically filled with steel punchings, again to get maximum density and cheapness. Continuing to follow the series of our videos, we looked at grades, of course. Rollover wasn't really an issue. Stability on grades, not really. More about that in a minute. And 2% was the maximum grade, so it was quite a stable vehicle, particularly when you consider the width of it. Now stability. I just said it's never going to roll over because it's so wide and so heavy and so forth. But we needed to consider longitudinal stability as well. And that might seem a strange thing to say because it's so long and so heavy. Towing tractors are generally tested through a load cell attached to a post embedded in the ground. That's how you get your actual drawbar pull figures. And you test every tractor to make sure the transmission is correct, gear ratios are correct, the engine's performing right, all of that stuff. We used to use a big steel post embedded in the ground and a pair of hydraulic cylinders with pressure gauges on them to measure it. And because we never got less than 0.8 coefficient of friction, we got some very high drawbar pulls. Conventional wisdom says your drawbar hitch should be as low as possible. Talk to any farmer, he'll tell you your hitch as low as possible to stop the tractor rearing. That situation exists with towing tractors. The hitches are as low as possible to try and line up with the aircraft nose gear. But what we found was we were still rearing. And it was quite unnerving to start with. The tractor behaved the opposite to what we expected. The limiting case was it would rear enough for a wheel to spin, and because there were free diffs all through it, the tractive effort or the drawbar pull would not increase. We believe it was happening that way because of the massive torques being applied through the wheels. That in fact the rear axle, let's say the rear axle, was coping with so much torque it was starting to lift the tractor. At a lesser coefficient of friction it would have been lesser result. It was never a safety issue, but it is something to be aware of, that high load, high torque vehicles may not follow the norm. And I'm going to talk about terramechanics. We talked about that as being the ability to cross the ground. Towing tractors always work on hard stand. They're definitely not suited for dirt. So from a vehicle point of view, the terramechanics is simple. You've got enough traction to go everywhere. However, we used to get a lot of inquiries from civil engineers designing parts of the airport, and they were always horrified when they realised the depth of pavement they would have to fit in order for the tractor not to sink into it or break it. It was also a problem during build in the factory. We had an older building. The concrete was a bit thin in places and it was not well supported. The foundations had sagged. We punched through the concrete floor a few times, so we ended up having to coat the build bays with steel plate. And we used to test the aircraft tractors going around the factory. We fairly quickly worked out not to drive over cast iron drainage grates. They really didn't like 13-ton wheel loads and would literally explode. We didn't want to explain that too much to the landlord, so we had a template made up for flame cutting a steel replacement. But terra mechanics problems don't just occur in the field. They can occur at your factory. Now the electrics were pretty standard 24 volt DC automotive electrics, except there were computers on board, one for the engine, one for the transmission, and we had to be fairly careful about how we protected those. This is where we learned about reverse polarity anti-sabotage protection. For cold climates, which was typically for us minus 25°C, we had to do some extra things. There were block heaters, hydraulic heaters, sump heaters, and battery heaters. And in the electrical enclosure, we fitted an incandescent electric bulb that provided just enough heat to keep it all warm with very low risk. They were powered through a wall socket. This is a Marshall self-ejecting plug. The right-hand side would be on the vehicle. The left-hand side would be to a power supply in a building. These are typically used for fire trucks, crash trucks at airports, that sort of thing, where people just need to jump in them and go. So when the vehicle drives away, the cable tightens and the plug mechanically separates from the socket. Works very well and saved a lot of trouble. What we learnt was that the steps we were taking would work down to about minus 50. Below minus 50, when it gets really cold, there were a lot more steps. Fortunately, we didn't have to take them. So for such a big, heavy, slow-speed vehicle, suspension was fairly straightforward. One of the axles was fitted with an equalising beam with a pivot pin, and it lumbered along quite nicely. We did on occasion put outboard wear pads, stainless steel wear pads, to take the load off the pin in a high traction environment. It was a simple, low maintenance design. So with a maximum of 2% grade and a 2% rolling resistance, braking is relatively easy. If you just detach the aircraft and let it go, it's going to stop of its own accord. So we didn't have to worry too much with braking. They were just drum brakes for service brakes and a dry disc on the input pin into the axle for parking, all hydraulically operated. The fluid power on board was all hydraulics. Pneumatics had been eliminated on previous vehicles as unnecessary. They used pressure compensated hydraulic pumps because of the steering system. We wanted to be able to provide very low steering effort at zero speed so that the tractors could manoeuvre better, and that worked well. Simple orbitrol steering valve too. It got a little more complicated with all the steering modes, but it was possible to just add additional valving to direct the oil to the right places. And if ROPS and FOPS, not required. Although the cabins did elevate hydraulically to give the drivers a better view, they weren't considered to be susceptible to falling objects. So now we have the basic design of the tractor. We know how heavy it is, how powerful it is, the transmission, the tyres, the axles, the hydraulics and so forth. It's time to start looking at the other ancillary things that are required for the application. Need to look more at the tow conditions. Are we ever going to face ice or snow? That's probably the primary condition. Are we ever going to operate on dirt? So what is the real limiting coefficient of friction? For aircraft engine thrust, it became an issue of what engines are fitted to the aircraft. It turned out that Pratt & Whitney's had a different thrust to General Electric's at idle, and that could be a problem. We could also have a problem if we were pushing back around a corner. There was one gate, I think in Singapore, that we had to push back uphill and around a corner, and the pilots of the aircraft had a tendency to start engines, jet engines, during the pushback. If they started the outside engine first, that could provide significant additional load on the tractor because of the lever effect. I've also struggled for many years because tractors are low height. Big ones are. And I've argued long and hard they didn't need to be. The reason that's been touted to me is that every 9 months they need to put an empty aircraft into a maintenance hangar that probably wasn't designed for it. So there's no space. So the tractor has to go under fuselage and push from behind the front nose gear. And hence the tractors need to be low height. The reality is that is an unladen condition that a small tractor could do the job. It didn't need a low height big tractor. Now height's an issue because in big high power things that are low height, you can't put an engine over an axle. And if you look at most on highway big trucks, the engines are in front of the axle with a transmission over the axle, or they're actually located over that front axle. Can't do that in low height equipment. But it seemed that fleet managers just wanted the same old thing. They wanted to not have to think about which tractor had to be allocated to which job. And as a result, they put up with a lot more cost and maintenance. I just mentioned hauling from behind the front nose gear. There are occasions where aircraft are hauled from the main gear. You hope that never happens because it generally means the aircraft has run off the runway. It's unlikely you would take a heavy towing tractor off runway to connect to it, so you probably connect with ropes and chains. There are other options that you should be aware of. Front cabin elevation. Yep, definitely. Even my little model Mitsubishi towing tractor has one cabin that elevates. It's only a single cab, and it's primarily a safety thing. There are very often rear driver's positions. That's where rear two-wheel steer came from. That's typically a stand-up driving position that's used for hitching up to the aircraft. There are sometimes rear cabs as well. We've talked about steering modes. There's a variety of them. I always tried to leave crab steer out because it got a lot of drivers confused, but a lot of people wanted it. It's purported to be the fastest way to turn the nose gear of the aircraft. Imagine a tow bar off here. You're basically moving sideways. So you are steering that nose gear very quickly. Whereas if you had to do it with 2 or 4 wheel steer, it's a much longer arc. And for a lot of tractors, we fitted integral lifting jacks, basically because the aircraft or the airports weren't equipped with large enough jacks to handle them. Looking wider, I learnt to be very careful of customer expectations. We had one major airline that insisted they wanted a cheaper, more cost-effective machine, and they were prepared to cope with a slightly lower spec. That was great. We built them, they were delivered, they were happy with them, and then they put them back to back with the previous supplied tractors, which were a high-spec machine. Surprisingly, for them at least, the new tractors got pulled backwards in that tug of war, and there was a hullabaloo about why these new tractors not better than the old tractors. Well, it's because you decided to be cheapos. You wanted something cheaper and less spec, you got it. Still did the job, not a problem. I talk about bragging rights in the pub. Could be bragging rights at the mosque, depending on your application, but buyers of this equipment like to think theirs is bigger and better than everything else. Logic doesn't apply, and that's a hard ask for marketing, sales and engineering to get it tweaked to meet all of those expectations. Oh, and of course be cheap. I'd say to you, don't undersize things. We shipped a lot of tractors export. We did not want warranty claims in Western China. It was just too expensive to go and handle them. Make sure you can justify the size of the components you fit and that they will survive in the field, even if the client is an idiot. At the start of this video, I distinguished from pushback tractors. And I said to you that I wasn't going to talk about pushback tractors because to me they're a bit chonky. When you don't use an engine in a continuous environment at a continuous high load, you can rate the engine much higher. The engine gets smaller. Same with the transmission, same with the axles. A lot of people didn't understand that, and they will buy a cheaper pushback tractor and use it in a towing application. A, it won't do the job. B, it'll break down. C, it's just a pain in the butt. So be careful about duty cycles and of the application. Aircraft towing tractors are all about grunt, the ability to produce it often over long distances. It's a heavy haul application. They are the ultimate hauler. So when you look at that tiny tractor under the 747, next time you're at the airport, realize it is a beast. It's a big, heavy, powerful monster. It has taken a lot of application engineering to get it smick. That's it on aircraft towing tractors. Come back again soon.